Today we're going to discuss about work and heat in thermodynamic processes. So first of all, let's talk about the difference between state variables and transfer variables. So what are state variables? State variables can be determined when a system is in thermodynamic equilibrium. For instance, state variables are pressure, temperature, volume, and internal energy. For instance, in mechanical systems, state variables are kinetic energy and potential energy. And in the case of a gas in a container, when we have internal equilibrium, that means that every point of the gas is at the same pressure and temperature. Now, transfer variables are related to not to the state of the system, but to the change in the state of a system. For instance, transfer variables are work and heat, and this happens, for instance, while energy is transferred to or from the system, for instance, a gas in a container. So work and heat can be either positive or negative, depending whether energy is entering or exiting the system in question. Now, here I have an example. I have a cylinder, and the cylinder is filled with gas, and we have the cylinder is closed with a piston. And in the first case, the piston is, the gas is in equilibrium, or actually in both cases the gas is in equilibrium, but in the second case the gas is compressed. Now here we can say that since the gas is at certain pressure and temperature, it exerts a certain amount of force on this piston, and the force is basically going to be equal to the pressure of the gas times the area of that piston. Now, if we take to compress the gas quasi-statically, so this is basically a quasi-static process, which means that we're going to compress the gas very slowly in order for the gas to be constantly at equilibrium. Because if the gas is at equilibrium at every point, meaning if we have a quasi-static process, then we can determine the state variables at every point. And in that case, we can plot them on a PV diagram, as we will see in just a moment. Now, if we compress the gas and the piston moves a certain distance, let's say dy, what we can say here is this. Now, the force or the external force vector, so basically F is a vector, we can express it as, let's see, minus F, or basically I can just erase this and we'll see. So the force vector is going to be equal to minus F times J. I will explain all of this in just a moment. And the displacement of the piston, or dr, R is a vector, is going to be equal to dy times also J. And then if you want to calculate the work that's going to be done with this system, we can calculate that d work is going to be equal to F vector times dr, or that's going to be equal to minus F times J times dy J. Now F here, or the force vector, we can express that as minus F, since we're pushing downwards in the negative direction, and here J is just a unit vector, meaning that this is a vector where the magnitude is 1. The same goes here. Now D here stands for differential. Now differential is a very small difference between values, so basically we're saying that the displacement of the piston is infinitesimal, and we have to express these as, since they're vectors. Now here we have the differential in work, so we're doing a very small amount of work for a very small displacement. Now if you can get a hold of this, now we said that F is equal to, let's do it like this. We said that F is equal to basically P times A. Now here in this equation we have minus F times dy. Now since F is equal to P times A times dy, here A times dy is basically minus F times dV, or a very small change in the volume of the system. Now when is the work positive and when is it negative? Now here we're talking about work that's being done on the system. So basically when dV is positive, meaning that when we have a positive change in the volume, then the work will be negative, meaning in that case that the gas is expanding, or work is done by the gas. And if work is done on the gas, then the work the work will be positive. Now, how do we calculate the total amount of work? Well, we can integrate both sides of this equation, and we'll get the work is equal to the integral. Now this is a definite integral, since it goes from Vi to Vf, V initial to V final, of let's see, and also don't forget the negative here. So this is going to be equal to, here we have P actually, of P times dV, and this is the equation for working in thermodynamic system. And basically this is the area under a PV curve. Now here we have a few PV diagrams, and as you can see, on the x-axis we have the volume, and on the y-axis we have the pressure. Now this curve here is basically the path taken, which means the path taken actually tells us the process that undergoes of the system, and the work that's being done is actually the area under this curve, or under these processes. Now, how do we calculate the work in all three cases? And of course we'll have to integrate P times dV, but we have to know the relationship of P in terms of the volume. What I mean is, we have to know the relationship, or we have to know the function of P in terms of V, because as we compress the system, the pressure not only increases and the volume decreases, so we have to know that relationship in order to calculate this. Now in the first two cases this is pretty easy, since here the pressure, in the first case the pressure is constant and the pressure is equal to I. So if we take I in front of the integral sign, what we will get for the work is going to be equal to this. Work is going to be equal to minus P of the integral of Vi to Vf of dV, and now work is going to be equal to minus P of, in brackets, Vf minus V initial. Now this is how we calculate the work in both of these cases. Since here, first of all, in the first case, the gas actually is compressed under a constant pressure from Vi to Vf, and then the pressure is increased from Pi to Pf. But here, on this section from Pi to Pf, when the pressure is increased under a constant volume, we do not have work is not being done since there is no change in the volume. Work is only done when we have a change in the volume. The same goes in the second case. So here we have the equation. In the first case, P is P initial. Since here P is constant, we're calculating this area under here. And here, in the second case, P final. And we're going to calculate the work that's being done. But in the last case, it's not going to be so simple, and the work that's going to be done will be between these two values, since the relationship between pressure and volume is not that simple to calculate. I will end this video here, and in the next part we will continue. Actually, we'll do an example to see that the work is not only, or the work and heat are not only dependent on the initial and final positions, but rather on the path that's being taken between them two.